So we're going to talk about momentum. So I want you to think about, envision an object that has a lot of momentum. Just think of something like, wow, that's got a lot of momentum. Got something in your brain? The cool thing with momentum is a lot of your initial ideas are right about momentum. This is very rare. Okay. Um, the variable for momentum, this is kind of weird, is a lowercase p. I think we're running out of letters in our alphabet. Okay. So that object that you envisioned, my guess is it has a lot of mass. Yes? That object that you envisioned also is moving fast. It has a high velocity. Okay? Mass times velocity. That's the equation for momentum. Pretty basic. Okay? Nothing crazy. Okay? So the more massive it is and the faster it's going, the more momentum it has. Good with that? Okay. So the unit for momentum, what's the unit for mass? Kilograms. And the unit for velocity? Meters per second. Kilograms times meter per second is the unit for momentum. So the first time we have not associated a scientist's name with this, like newtons or joules. We just leave this as kilograms meter per second. I don't know why that got the short end of the stick, but whatever. Okay, so kilograms times meter per second is the unit for momentum. Is momentum a vector or a scalar? So mass, is that a vector or a scalar quantity? Does it have direction? Does not have direction, therefore it's a scalar. Velocity, is that a vector or a scalar? It is a vector. It has direction. Okay, so momentum also has direction, and it's the same direction as velocity. So it is a vector. Same direction as velocity, which is nice. Momentum, the direction of velocity, I think it's pretty intuitive. Like it's moving this way. That's the direction of velocity and momentum. Moving this way. That's the direction of velocity and momentum. It's not like acceleration. Okay. But that detail is an important detail, the direction. Okay. So describing momentum, if you were going into a series or a tournament against a team that was going into that tournament with a lot of momentum, if you're going against them, would that be a good thing or bad thing for you? Bad thing. Why?
Because
they've had a lot of wins. Like it's going to be hard to stop them. That makes sense? Okay. So how hard it is to stop something. is a way to think about momentum. Okay. If something is stopped, how much momentum does it have? 0. How hard is it to stop? It's not. It's already stopped. Okay. Another way to describe this is inertia in motion. An object at rest wants to stay at rest, but an object in motion wants to stay in motion. Okay? And the more inertia it has, the more mass it has, the greater the tendency is to continue that state of motion, of moving. Okay? And you see the similarities between momentum and inertia. Okay? Good there? All right. If the net force on an object is equal to 0, so the sum of the forces are equal to 0, what would happen to the object's momentum? I want you to think. If the net force acting on an object is equal to 0, what would happen to the object's momentum? Tell your neighbor.
Yes, they would put it there.
And tell your neighbor what would happen if the unbalanced forces, if the forces were not balanced. Some of the forces are not equal.
Yeah.
Okay. If the sum of the forces are equal to 0, then the momentum of the object stays constant. Good with that? And the momentum, if the sum of the forces are not equal to 0, the momentum changes. How are we doing there? Okay. So then that kind of begs the question. Okay, so if an unbalanced force acts on an object, momentum changes, how much does it change by? Could we put a number to that? Could we quantize that? Quantify it. Okay. So let's start with something that we are familiar with. Actually, before we do this, so we assume that momentum is going to change, right? If a net force acts on it. Okay, so that's going to be final momentum minus initial momentum. Change in, okay? When we do this, we're going to assume in this class that the mass of the object doesn't change. That the mass of the object stays intact. It's not like we're walking around and all of a sudden our arm falls off like, oh, man, I hate it when that happens. Okay, so the object stays intact. So if the mass stays the same, we can say that the change in momentum is equal to mass, which stays the same, times a change in velocity. You all right with that? Okay. All right. Back to Newton's second law. When we were first learning acceleration, what was the equation? Acceleration, close. Velocity over time. Yep. The rate at which velocity is changing. You good with that? So if I take that, stick that here, I've got mass times change in velocity or change in time. Check this out. What is that that I circled in blue equal to? Tell your neighbor. So what that is change in momentum over time. All right with that? This is actually how Newton wrote his second law. It wasn't F equals ma. It was net force. The total force is equal to the rate at which momentum is changing. How quickly momentum changes is equal to the net force. Okay. So we can take this equation and we can answer the question, if a force acts on an object, how much will its momentum change by? Well, if we take the force and multiply it by a certain amount of time that the force was acting on it, that equals a certain amount of change in momentum. You all right with that? So force multiplied by how long the time at which the force acted on it equals how much momentum changes by, equals the change in momentum. Good with that? Which this is the change in momentum, or the impulse momentum equation. Which says the net force times its time is equal to change in momentum, which for this class is equal to mass times change in velocity. We give this a name. Force times time, impulse. This has a very similar feel to the work energy theorem that we just had. We said, okay, don't copy this down. This is just questions. Last chapter, we said, force. I bet that affects energy. I wonder how we could make force related to energy. And so we said, okay, force times distance, that's going to be equal to a change in energy. We're going to call that expression force times distance, how strong the force multiplied by how long the force, like the distance the force acted on it. We're going to call that work. Okay, this is distance based. This one's time based. Have a force acting on it for a certain amount of time. That's going to cause change in momentum. We're going to call this quantity impulse, just like we called this quantity work. Good with that? These are not the same thing. They're just some, you can see some similarities. Okay? Oh, deleted that. All right. The unit for impulse. What's the unit for force? Newtons. What's the unit for time? A Newton times a second is impulse. But I thought that that's equal to change in momentum. Isn't that like kilograms times meter per second? Yeah, it is. So a Newton comes from mass times acceleration. Mass, kilograms, acceleration, meters per second squared. Times seconds. How does that simplify? We're left with kilograms times meter per second. Okay, so a Newton times a second is the same thing as a kilogram times meter per second. Good? All right. Good. Questions? Tell your neighbor.
Are they both going 20 miles or 20 meters per second? Okay, so just to make sure, you have to equal the, you have to.
Okay, correct answer is?
Yeah.
How is it possible?
If the sports car speeds up to the mass.
Okay. Yep. If it was going fast enough, the sports car could have the same momentum as the Mack truck. Okay. Here's what I want you to walk away from. Momentum is not solely how massive it is, and it's not solely how fast it's going. It has to be the combination of the two. You get with that?
I'm watching Carlson's class. So.
Okay. Sounds good. I will. Yep. Yep. Have a conversation.
No, no. This has bigger momentum. It'll hit the ground the same. The bowling ball will hit harder than the.
Correct answer is? Correct answer is C. Both have 9.8 meters per second squared. Both will, because of that, have the same speed, but the bowling ball has more mass, therefore it has more momentum. Okay. All right. Call that again.